Okay, let us go to the last part of today, which is on theorems on limits, and we will see that this LTS limit through sequences theorem is very important, and it is a striking shortcut, at least for some results. So the title is now Theorems on Limits, basic theorems. So one starts as usual by the uniqueness of the limit. First, uniqueness. So this is the first theorem we prove. And the statement is the following. As usual, we have a subset of R that I call E, which will play the role of the domain of our function. X bar is an accumulation point of E, F from E. This is a strange defect of this new iPad. From E to R. Then let me write it like this. The limit of f is equal to L, and limit of f for x going to x bar is equal to L prime, then L is equal to L prime. Okay? And of course L and L prime are in R bar, so both convergent and divergent functions. So proof. Consider a sequence xn in E minus x bar, with xn going to x bar, then by limit through sequences first part, so from the limit of function to the limit of sequence, we have that f of xn tend to L and f of xn tend to L prime. Why the first it tends to L? This is true since, limit for x going to x bar of f of x is equal to L. And this is since the same limit equals L prime. Now, by the uniqueness of the limit of a sequence, we have L equal to L prime. End of the proof. We do not have to use neighborhoods or epsilon, something like that, because we substantially download the proof of the uniqueness of the limit to the of subfunction to the uniqueness of the limit for sequences that we already know. Second theorem, permanence of sine. This time we use the metric definition. Use the metric definition because it's simpler, it's shorter. Okay? So, again, as usual, E subset of R, x bar is an accumulation point of E. F goes from E to R. And we have that the limit for x going to x bar of f of x is equal to L positive number. Then there exists some U in a neighborhood of x bar such that for every x in U and also in the domain but not equal to x bar, which is always excluding when we talk about limit, then f of x is larger than 0. Okay? Proof. Here the proof is identical to the proof we used for sequences. So take epsilon equal to L. Since the limit for x going to x bar of f of x is equal to L, then there exists U, neighborhood of x bar, such that whenever x is in U intersection A, E minus x bar, we have that f of x minus L less than L. The distance is less than L, which means that 0 is less than f of x less than 2L. So what is important here for the permanent of sine is this part here. Okay, end of the proof. And as usual, we have a corollary. Sorry. If f is positive in a neighborhood of x bar and lim for x going to x bar of f of x exists and is equal to L, then L is greater or equal than 0. Remember the equal here. I already discussed this equal when studying sequences, so I won't do it again, but this is the point. Okay, other remarks to be sketched here. Are the following. F negative, so if L less than 0, then there exists a neighborhood of x bar such that for every x in U and E but not equal to x bar, f of x is negative. Vice versa, if it was my professor who wrote vice versa as 2 words. I inherited it from him. He was an Indian guy, very, very nice. And they wrote vice versa. And as a students, we laughed a lot. Aha, vice versa. And now I'm doing that. So this is a joke of life. Never laugh of your professors, because you will become as them when you get older. Okay, vice versa. If there is a neighborhood, so if f is negative, in a neighborhood of x bar, and there is a limit for x going to x bar of f and is equal to L, then L is non-positive. Cannot guarantee that this is strictly negative. This is in general not true, but it is surely non-positive. Other remark, the conclusion holds for L equal to plus infinity, but it is really trivial. If the limit is plus infinity, then the function is positive, strictly positive in a neighborhood of x bar, and also minus infinity. So this is a word, language. If you say glossary, if a property of a function is verified only in a neighborhood of a point, we say that it is verified locally. Locally, it is a very important word. Okay? If it is verified everywhere, whatever everywhere means, we say it is verified globally. So, philosophically, conceptually, locally, in the case of functions, in the case of limit of functions, the word locally plays the role of eventually. In the case of sequences. So stop relaxing and go for theorems, and the third theorem is the theorem of the double comparison of two policemen. E subset of R, x bar is an accumulation point of E. And then we have three functions, f, g, h from E to R, such that for every x in E, f lies between g and h. Moreover, the limit for x going to x bar of g of x is equal to the limit for x going to x bar h of x is equal to L in R. So exactly like in the case of sequences, here and here, you have two functions that go to the same limit L. So they force f to go to the same L too. Okay? L is finite. For infinite case, you just need one policeman, not two. However, proof. We do it by sequences. Why not? So let xn be an arbitrary, or so to say, a generic sequence with values, as usual, in E minus x bar, and such that xn goes to x bar. Then, for every n, one has g of xn less or equal f of xn less or equal h of xn. Now, for the first implication of the theorem LTS, limit through sequences, I say again 1, we have that g of xn inherits the limit from the function, so it goes to L, and h of xn goes to L too. So by double comparison for sequences, we have f of xn goes to L. But now we use LTS in the other direction. Since the sequence xn is generic or somewhat arbitrary, then we have that the second part of the theorem of limit through sequences, that is here, every sequence gives rise to images that converge to L, every sequence. So we can use LTS2 and conclude that the limit for x going to x bar of f of x is equal to L. And this is the end of the proof. Wonderful. So, and here you see how these theorems are sort of shortcut, but these theorems were short also in their original version directly made for functions. But let us go to the algebra of limits. Of functions. You know that it is the same, it is the elementary one, the same as for sequences, but how to prove it? Do we really need to rerun through the same details? So, the hypothesis is, as usual, that you have a set E, subset of R, x bar, accumulation point of E, G, F, are two functions defined in E with values in R, and the limit for x going to x bar of f of x is equal to L, while the limit for x going to x bar of g of x is equal to k. Then, first theorem says that the limit for x going to x bar of the function f plus g of x, that is defined elementary, I really don't need to specify that, but just to be complete, which is f of x plus g of x, this limit here equals L plus k. I give you the proof of that. Proof. So I consider a generic sequence xn with values in E minus x bar, and such that xn converges to x bar. Generic. A generic sequence made like that. Again, it exists because x bar is an accumulation point of it. Then we consider the LTS limit through sequences theorem that says with the first direction that f of xn converges to L and g of xn converges to k. Then the sequence f plus g of xn that equals by definition of sum of functions f of xn plus g of xn will converge by the algebra of limit of sequences that we already know. This converges to L plus k. Sum of limits of convergent sequences. Then, by limit through sequences second point, using the arbitrariness of the choice of xn, we have that the limit for x going to x bar of f plus g is equal to L plus k. End of the proof. Wonderful, no epsilon halves. But again, this proof was simple also in the original version, but then we go to the product. And if you remember well, product was quite complicated and ratio was still more complicated. So, as a homework, by the very same, it is almost identical what you have to do by the very same procedure. Prove that the second theorem is lim for x going to x bar of fg of x with the same hypothesis I wrote before. This is equal to Lk third. Lim for x going to x bar of Cf, where C is any real number of x, is L times C. Fourth, with k different from 0 and g not identically 0. No, it is not true. Let me be a bit tougher. Different from 0, at least in a neighborhood of x bar. We can weaken this hypothesis, but it is not so important to be optimal now. Okay, let me say in a neighborhood. Otherwise, one has to redefine the domain. Really, really useless. In a neighborhood of x bar, then we have that lim for x going to x bar of f of x divided by g of x is equal to L over k. Homework, prove that. And moreover, the theorems, so the algebra with plus and minus infinity follows the same rules as for sequences. So you have Lk in R bar. So first, plus minus infinity plus x is equal to plus minus infinity for every x in R. Second, plus infinity times x is equal to infinity times the sine of x. If x is negative, it becomes minus infinity. For every x in R and non-vanishing. Third, minus infinity times x is equal to minus infinity sine of x. Again, for every x in R minus 0. Fourth, forms like plus minus infinity times 0, infinity minus infinity, 0 over 0, have no given determined result, have no a priori result. Therefore, they must be studied case by case. A word that is often used, I don't like this word, but I know you use it, so I will sacrifice myself. So it's indeterminate forms or indeterminacies. But it really does not mean anything. It means that you just have to study the limit. You cannot rely on the algebra. And let me give you some examples. Yes, I have to give you these examples. I cannot. So, first example. You have f of x equal to x to alpha divided x to beta in the limit alpha beta larger than 0. We want to study it for x going to 0. So, first case, if alpha is larger than beta, then f of x is equal to modulus of x to the power alpha minus beta. This goes to 0. Second, as alpha equal to beta, then f of x is equal to modulus of x to the 0 power. This is always equal to 1, so this is constant and its limit is 1. Third case is alpha is less than beta, then f of x is equal to x, to 1 over, let me say, x to the power beta minus alpha, and this goes to plus infinity. So you have to know that if you want to prove that. Second example, very important, is the following. We take the limit that defines E, but we go for functions, and the result is always E. This is because, as you already studied at exercise session, for every an going to plus infinity, such that an going to plus infinity, we have that 1 plus 1 over an to the power an goes to E. So by limit through sequences 2, you end up with the result. Third example, which is very important too, and then and then this is the last topics of today, is the limit for x going to 0 of sine of x over x. Okay? Of course, both sine of x, for the exercise I performed some videos ago, sine of x goes to 0, x going to 0, so we are in an indeterminacy. It is not covered by the algebra, so we cannot rely on the algebra. So, what can we do? We can do a geometric construction, which is the following. Oh, let me try to be like Giotto and draw in a perfect circle. Yeah, and now I move it, and it's wonderful. Nice. Okay. Okay. Now, let us consider this construction. Here you have an angle x. This is x. And here, this is sine of x. This purple guy is sine of x. Okay? I also use some colors in order to be clearer. Here there is horrible, 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 horrible. Very horrible. Okay, it is a defect of this guy here. Let me start again. It goes to the rubber in a completely autonomous way. So let us try again with the circle. It was an awful circle, but okay, good, more or less, good. Again, angle x. Sine of x, purple. Good. Then the chord, black. Okay, this time I survived. And then let me also do this vertical guy here. And let me put letters wherever they will be useful. For instance, O is the center. Traditionally, I call it A, B, here. This is C, and this is D. And more or less, we are here. A is 1, 0, because the radius is equal to 1. Okay? Now, x is larger than 0, and so on. So, here we have this, here we have the triangle OCA, this triangle here. This is included in OCA, the sector here. So let me write it in this way. OCA triangle included in OCA sector. I hope it is clear. Which is included, of course, in the huge triangle OAB. This is OAB. Of course, OCA sector is included in the huge triangle OAB. If you have an inclusion, then you immediately go to areas. So you have that the area of OCA is smaller than the area of OCA sector, which is smaller than the area of OAB triangle. Okay? Now, what is the area of OCA triangle? So, OCA is a triangle which has a basis. The basis OA is equal to 1. The height is sine of x. So, 1 times sine of x divided by 2. So, this is sine of x divided by 2. Okay, here we're using that x is larger than 0. Now, what is the area of the sector OCA? You perhaps don't remember what is the area of the sector of angle x, but think of the sector of angle 2 pi, which is the whole circle of radius 1 as an area which is pi. So if the angle is 2 pi, the area is pi. If the angle is x, the area is x over 2. So sine x over 2 is less than x over 2. And this is an inequality which is well known. And then OAB. What is OAB? Is the beast, the huge. The huge triangle here. So, and here, what you have a triangle, rectangle, so you have to multiply the two shorter sides, this guy here and this guy here. This guy here is 1, while this guy here is the tangent of x, because in order given a side here in a triangle rectangle, in order to find the other one, you have to multiply it, which in this case, fortunately, is 1, by the tangent of the angle. So this is less or equal tangent of x divided by 2. Okay? So just cancel the divisors 2, you have sine of x, less or equal x, less or equal tangent of x. So to say, sine of x, less or equal x, less or equal cosine of x divided by sine of x. Reverse it. Since x is positive, then you can write or not, divide by sine of x. You can do like that, and you have 1 less than x divided sine of x divided by less or equal, 1 over cosine of x, because here I was wrong. I start being tied, and now this is the tangent. The tangent is not cosine over sine, but is sine over cosine. And then, finally, you have, just to reverse it, that cosine of x less or equal sine of x over x less or equal 1. And this is the end, because cosine of x goes to 1. This is an exercise I gave you as a homework in a previous video. 1 is a constant, it goes to 1, so this goes to 1 by double comparison. Of course, you have, as a homework, proved the same conclusion for x less than 0. you end up by this very important limit. Sine of x divided x is equal by 1. And here I stop. So, see you tomorrow.